Welcome everyone to today's web seminar. My name is John Hay from University of Nebraska. Also presenting with me today is going to be Eric Romick from Ohio State University, and we'll do some formal introductions in a moment. Today's web seminar is on solar economic analysis, and this is a web seminar that if you're here to get the overarching big picture, that's not necessarily what we're here for. We're here to get into the weeds. We're going to get into the details, and I hope that's what you're looking for. This web seminar is sponsored by the North Central Region Sustainable Ag Research and Education, so North Central Region SARE. Eric and I received a grant to do some professional development work on solar economic analysis. So our core audience in this is other extension educators, rural bankers, USDA, rural development, USDA, other personnel, and generally people that work with private citizens that are interested in solar. If you're a private citizen interested in solar, you're also welcome today. We're going to get into some really good detail on solar economic analysis and talk through that over the next 4 web seminars. All right, here's our top slide here, and you can see the North Central Region SARE logo and the names of our presenters. So if you have any questions in detail you'd like to ask us, here's our information. You can also find it on our registration page where you registered. But my name is John Hay. I'm here at the University of Nebraska. I've been teaching on renewable energy and biofuels issues for the past 12 years. And I got into solar about 6 or 8 years ago, and really did a lot of self-study. But to get in depth, I made friends with a solar installer and have helped install systems 4 to 5 a year since for the last 6 to 8 years. So I've done some hands-on work. I've installed my own system at my own home about 4 years ago, and this has really become a passion of mine to not only learn about solar, but also to teach others and to do a good job understanding what they can actually do and what can't they do. So I tell people that somebody makes a decision to install solar or not, if they make it with good information and good data, it doesn't bother me that they don't install. The fact is that they were able to make that decision using good information. Eric, I'll give you a moment to give a brief introduction.
Thanks, John, and good morning. Welcome, everyone. My name's Eric Romick, and I'm an Ohio State University Extension Field Specialist for Energy Education. Much like John, I've been working in the world of energy for probably 12 years now. My first experience with solar energy was back in 2008, working with a utility scale solar project in Northwest Ohio. It was kind of the first of its kind after our state renewable portfolio standards were passed. And so worked with the local community and developers and the contractors alike on the construction of an 85-acre solar field in Northwest Ohio. And so from there, really kind of transitioned to a lot of projects like what we'll be talking about today, and focusing more on working with farmers and small businesses to analyze behind the meter projects. And just like John said, really looking at it from a decision flow standpoint, really trying to get the right information and understand, is this project a good investment for my business or for my farm, and making sure that we're understanding the details of the project so that it performs like you expect it to. And everybody has different metrics for success, right? There's different motivation factors, and we recognize that. And John and I do our best to try and understand what are the motivations of folks that we're working with, and helping them understand how the project's going to work for them. So it's been a lot of fun. John, I've been working on this topic for 3, 4, 5 years now, and really starting to help folks understand different resources that are available to help them make these decisions. And we're excited to share some of the modeling tools with you the next couple weeks here as well.
All right, great. Thanks, Eric. what we're going to do is present over the next 4 weeks or 2 weeks, 4 sessions. If you can attend all of them, that would be ideal. If you can't, we are going to record these and try to make them available so you can watch them at your leisure to get caught up. We're going to start today with some of the basics and kind of tease you with some of the modeling. Then we're going to go into costs and financial parameters in detail, incentives, which is also very important, policy and electric rates. And then finally, we're going to go through actually modeling a system and a case study in great detail on the 4th session. And hopefully, if you follow along well, you'll be able to perform some of those models yourself with some of the free software that's out there. And do some of these analysis yourself with you and your clientele, and understand the inputs and the outputs. And that's really the big part of this. So even if you don't do modeling, understanding what goes into that analysis is going to give you a lot of good information. Today, we're going to get into some of the basics of solar. And then we're going to follow up with this intro to the System Advisor Model, which is going to be kind of a teaser. We're going to go through it kind of quick, but you're going to see some of the inputs and outputs. And then we are going to do a group discussion, which is going to be kind of an online type of discussion. So we don't actually have to all be talking, but I'll introduce that as we get there. If you have questions as we go, there is a chat box. Go ahead and use the chat box, and either Eric and I will be watching that. And so that we can try to get to those questions, because this really is about your questions. I'm going to present the first part of today. Eric's going to do the second half, and then we'll kind of all do the group discussion at the end together to finish up for today's session. So as we go into the intro, I want to just give some brief definitions quickly. First of all, when we think about solar, there's different sizes. And I'm going to separate those sizes into just 2 large categories. What I'm going to call distributed solar, which is small scale, typically under 100 kW. It's grid connected. It's usually behind the meter. And so it's usually at a load, a business, a farm, a home, and it's behind the meter where that load uses it first. It's usually customer owned. And again, like I said, the energy is used first by the customer because it's behind the meter, then may go out on the grid if there's excess generation. There are situations where distributed generation could be all going directly to the grid. That might be the case of a community solar or something like that. I'd still call that distributed solar. Utility scale is large scale, typically over 100 kW, but jumps very quickly into the megawatt scale, over 1,000 kilowatts. And those are what we might call a solar farm. Large scale, utility or investor owned, probably investor owned mostly because of the tax credit. Grid connected, electricity is flowing to the grid, and then the electricity's value is based on contracts and the marketplace. Versus in distributed, it's the value of electricity is based on the electric rate structure of the load, also the policies and other things involved. So these are quite different. We are going to focus predominantly on distributed solar. We both have some experience on utility scale, but we're focused on distributed solar because that's what really applies to residences, farms, and businesses, which is our overarching goal for this series. I threw this one in just for fun. This is steps in the solar PV process or solar electric process for a home. I threw this in. I created this when I put in my own system to kind of figure out what were all the steps included. And really what we're focused on the next 4 sessions is number 1 and 2, particularly number 2, where I'm including this solar analysis as part of like the solar homework. Efficiency is always the most important thing, where a home or a business should always look into efficiency before they look into renewables like solar. But once we've done all the efficiency, then it may be time to start looking into bigger things like solar and see if that's going to work out for you. And so that solar homework and goals, and then maybe even number 3, getting quotes and things, we're going to get into some of that stuff. The other sections, typically are done by the installer. Number 5 through 15 is essentially all the installer is going to do. Unless you're doing your own, the installer is going to do those. And so really the business owner, homeowner really should be interested, should be paying attention to 1 through 3. And then finally, they're after 18 and 19, they're the ones that are going to be living with it. So that's kind of the steps in the process. Really, when it comes to solar economic analysis, we have to think about what is making us money. What is, or saving us money in this case. Saving money is making money, but I'm going to equate this a little bit to corn. I'm an agronomist by education until I switched to energy. But when we think about corn, we need both the yield of the corn and the price of the corn. And that's what's going to make us money. If we have one of those but not the other, it doesn't go real well from an economic standpoint. If I had high corn prices but no yield, or if I had very high yield but very low prices, I kind of need a mix of both. And so when we put up solar, we obviously have to generate electricity to even begin to make money. So if it doesn't generate, if I put it under a tree and it doesn't generate, it's not going to do any good. If I put it up in a place and get a very low rate for electricity, it could generate quite a bit, but I'm still not going to probably make very much money or very quickly. And so what we need to understand is what is the value of that electricity? What's the price of corn? And we have to estimate how much we're going to yield. And luckily, better than corn, I can estimate my solar yield of electricity much more accurately than I can estimate my yield of corn on any individual year. But on a long term, I can estimate my corn yield, but not very good on a year-to-year basis. Let's touch on some terminology real quick. The overall system is typically called the solar photovoltaic array, photovoltaic meaning sunlight to electricity. Each individual solar panel is called a module. So if you went to buy a solar panel online, the industry calls it a module. You're going to search solar panel. They're going to bring up the price of modules, because the industry calls a solar panel a module. In everyday language, you can call it either one. People understand what you're talking about. Within the solar module is a number of cells. Typically, cells have been about 6 inches by 6 inches. And then the solar module has between 60 and 72 cells. Some of the more modern cells, though, have been cutting these, or some of the more modern solar panels have been cutting these cells into thirds and mounting them on the solar panel in chunks rather than whole cells. And it's caused them to look a little different, but they essentially function the same way. They're doing some new and unique things with solar cells now by cutting them into pieces, and they look a little different. But this is a solar cell. And within that solar cell, the most common chemistry of that solar is silicon-based solar cell. Now, this could be a cadmium telluride or other types of things, but they still function very similarly. What we have is a crystal that absorbs light and has some function of the sunlight being able to activate and give energy to the electrons. In this case, silicon is that crystal. So silicon as a crystal is there, and there is something special about silicon where if, I'm just going to draw on my screen here, if the sunlight came in and hit one of those electrons, the electron can just move around in that silicon crystal. That's the electrical property of a silicon crystal that's very special. It can not only absorb light, but that electron will flow through that crystal fairly freely, but it doesn't know which way to go. So it just is random. And so the people that build solar cells put in impurities in the crystal to create an electric field. And so that's what we're putting in here, phosphorus and boron. So phosphorus has an extra valence electron giving it a negative charge. Boron has a fewer valence electrons giving it a negative charge. So as we put those in, an electric field is created in that inside that crystal. A net negative charge on the phosphorus side and net positive charge on the boron side. Those charges pull on one another and essentially end up creating an electric field in the center called the PN junction, a positive negative junction within that solar cell. This is where the fun stuff happens, where we're going to put in a metallic contact. We're going to put in a little tiny wire that's going to catch those electrons now that they know which way to go, because there's an electric field now. Now they know which way to go. We're going to throw a photon in there, and the electron is going to flow through the cell, giving up its energy to the load, and then flow and fill in. So no electron was harmed in this process, right? It was just simply given energy. The energy was taken from it in the load, and then it refilled. So if we watch that again, we'll see the electron get excited, flow to the positive side, and then go slower on the backside because it doesn't have as much energy. I'm going to throw another little detail in there. There's something else going on this slide. Let's watch it again, see if we can see it. Did you see that there's this red thing that's going the other direction? The red that's flowing in the other direction in this case are actually the holes left behind by the electrons, and they flow in the opposite direction of the electrons. And in the early days of understanding electricity, observations were made, and they were made by people we've heard of, like Benjamin Franklin. Benjamin Franklin made an observation that of what he suspected was the directional flow of electricity, was the electric current. And he said electricity flows from the positive side to the negative side. And his observation became what we use today and how we label electricity. And his labeling was actually not the flow of electrons, but was the flow of the holes. So the positive side is the side with the holes. The negative side is the side with the other side. And we actually call the electricity flow, the current is the flow of the holes. It seems backwards, and it is, but as long as we all agree on which side it goes, that's the way it's labeled. So a little just electrical background there for fun. But now we know we have a cell that has a flow of electricity when it's exposed to sunlight. There are three types, very common types of silicon solar cells. There is monocrystalline, where they grew one large crystal and sliced it. And you can see that one is very, very solid colored, versus the one in the middle is polycrystalline, where they let a large mass of silicon metal cool, and then they sliced it, and the crystals were formed in all different directions. And it kind of has a little bit of a iridescent kind of look to it. And then finally, there's thin film, where they're just almost kind of layering those. Almost you hear about solar printing. It's that type of a system. Monocrystalline are more efficient than polycrystalline, which are more efficient than thin film. And both mono and polycrystalline have long lives, while thin film is not quite as long-lived, doesn't last quite as long. A lot of people say, well, that means I want monocrystalline. I say, well, maybe. What's the price per unit power? Really, if you can get a price per unit power that's low, having it be just slightly less efficient is okay, especially when space isn't limited. I'm not trying to generate a certain amount on a certain small roof or something. If you have a small roof and want to maximize production, a monocrystalline is going to be able to do that for you. If you're just trying to offset some of your load, the price per watt, lowest price per watt, is going to be what you want. Eric, if you want to read those chats and let me know if we want to cover them, we can do that. What I pulled up here is just a spec sheet for a solar panel. Go ahead, Eric.
Yeah, the First question is, why do they cut the cells into pieces?
The fact is that we've got to increase the voltage of a solar panel. And so what we do is they cut them into pieces so that they can wire them in series to increase the voltage. Because if we have a solar cell that's only a partial volt, maybe a half a volt, and we put 4 of them in series, we're at 2 volts. And we can increase the voltage by wiring them in series together. And that's essentially one of the reasons why they're going to cut them into pieces rather than having larger cells. And they're beginning to cut them into smaller and smaller pieces to work out the voltage and the things that they want. So those are some of the reasons. The monocrystalline, it's very tough to grow a very large crystal, so that they grow those crystals and then slice them, and that's about as big as they can get, or they want to get, I suppose, from an economic reason. They limit that size to about that 6 inches by 6 inches. Good questions. I brought up some of the properties of a solar module or solar panel, and I want to point out just a couple of things. One is that on the top here, we have the standard electrical properties under STC, standard test conditions. Standard test conditions are kind of laboratory conditions. We have a set amount of sunlight, 1,000 watts per meter squared. We have a specific temperature of 25 degrees C. We have an air mass of 1.5, essentially saying how much atmosphere is between the solar panel and the sun. And I think, and then also I think there's one in there where the sunlight is coming in at a 90-degree angle into the solar panel. And so under standard test conditions, it will generate, there's 2 solar panels here, but we'll just use the one on the right. It will generate 300 watts of electricity under standard test conditions. But in the real world, it does not see standard test conditions very often. The temperature is above or below 25 degrees. The sun is above or below 1,000 watts per meter squared. The air mass is, higher or lower than 1.5. And it does not see that. So the real world conditions, it generates less electricity than that. And so a closer estimate is under nominal cell temperature. Nominal cell temperature. I don't remember what the O stands for in that case, but nominal operating cell temperature. And so 220 is about what that is rated. Now, when we see a solar panel, we almost never get to find this number unless we pull the spec sheet. So we base really everything off of the standard test conditions number, because that's the number that we know. And when I say I have a 4 kW solar array, I'm using that based on the standard test conditions number. So just a little background about when we think about numbers, we're basing it on standard test conditions, and we're not likely going to see that very often in the real world. So I'm going to give you a little equation here, and if you take this to heart and use it, you will use this quite often just in your everyday life because it's fun. And what I mean by that is you're going to drive by a solar array and you're going to count the solar panels and you're going to estimate how much they'll produce in a year. And you can do that just with your phone calculator once you've learned how to use this simple equation. So what we're going to do is we're going to estimate the standard test conditions of that, the standard test conditions capacity of that system. And we're simply going to do that by either knowing it, or we're just going to count the solar panels and then apply an average rating capacity for those solar panels, which about 300 is pretty good for most solar arrays put in today use 300 watt panels, up to maybe 350, but a lot of them are in that 300 to 320 range that are installed right now. So you can use that as a base number. We need to know how many hours of sunlight, but not just sunlight, because we get a lot of sunlight, but sometimes that sunlight it's early in the morning and it's not very useful to us. It's cloudy on some days, it's rainy on some days. And so we're going to use a number called the peak sun hours, where they take the total solar irradiance in a day, and then they figure out how does that look to kind of normalize it to 1,000 watts per meter squared. So on average, how much irradiance, if it was 1,000 watts per meter squared, does a location see on an average day? Now, we want this as the average for the whole year. And so it's fairly simple to get by going to some of the websites. I'm going to show you that in a second. We're going to multiply by 360 days in a year because we want to know how much will it produce in a year. We're going to derate that to the real life conditions, because remember, we don't know the nominal operating cell temperature conditions, that derate. So we're going to naturally derate that between 20 to 30%. So we're just going to reduce that number to take into account that it's just not going to see that very often. So I did an example below. A 10 kW system times 5 peak sun hours times 365 derated by 20% gave me 14,000 kilowatt hours a year. So if we look at a peak sun hours chart, if I'm here in Nebraska and I say I live maybe in southeast Nebraska, I want to use a number somewhere between 5 and 5.4. If where Eric is in Ohio, we might, it's somewhere around there. He's going to be somewhere between 4 and 4.4. And that's why in that previous example, I used the number 5. And as you get into higher solar irradiance parts of the world, they're seeing more hours of sunlight. They're seeing more hours of sunlight not only because of maybe it's hotter, or they have more hours a day because they're farther south, or something like that, but also because they have less rain. And so they're seeing less cloudy days. So those solar irradiance are based on like 15-year averages of actual measured solar irradiance. And so the climate and weather are taken into account for those numbers. So let's do an example. You drove by this one and you safely slowed down so you could count the panels. And so you counted the panels and you found out that there was 48 of them. This one's on a farm north of Lincoln, and we installed it as a workshop a couple of years ago. This was our volunteer crew that installed it as a workshop as a learning experience. Each of those are 300 watts. We multiply 300 times 48, we get 14,400 watts, or 14.4 kW. We take that times 5 peak sun hours because it's in southeast Nebraska. 365 days a year, 0.8 derate factor. Looks very much like the equation I just ran. I used the same numbers, same derate factor and everything. I came up with this system will generate 21,000 kilowatt hours a year, approximately. Now, I'm going to tell you, it doesn't always work out this close, but year one for this system was 21,694 kilowatt hours. So we were pretty darn close on that estimate. That estimate is very rough, but it's also very powerful because it gives us kind of a benchmark of how much a solar array will generate in a particular place in a particular year. And it's super fast and super easy. And it's going to be within about at least 5 or 10% in most cases. This is obviously making some assumptions, making something that there's no shade. We're not having any shade issues and things like that. We're assuming that it's facing south at a fairly reasonable tilt angle. We'll get into some of those details on Thursday of this week of how those affect. Yeah, go ahead, Eric.
That's also, I really like using that formula with folks that call, and a lot of times they just have general questions about what size system would I need, based on my usage, and they just want to get that information before they really start the development process or really start talking with an actual installer. And that's a good way that they can kind of just do some back of the envelope calculations based, pull your electric bills and see what do I use over the course of the year, and how big of a system would I need to meet my goals. And so that's where I see that formula used a lot, is pull your electric bills out, kind of do some calculations like this to determine, okay, what size system would I need? And then make that decision on, do I really want to investigate further whether or not it makes sense to put a project in?
This is a great thought. And let's just do it real quick here, that example. So we're going to get into the details of why the sizing is this way later. But let's say a house used 16,000 kilowatt hours a year. We don't probably want to generate all of that with solar, because there's reason that economically is probably not the best thing unless you have very green motivated. So we want to produce about maybe somewhere between 50 and 75% of that. So let's just say we want to generate 10,000 kilowatt hours a year is what our goal is. So then we simply substitute in our 10,000 kilowatt hours here and solve for X, or kW. And that will tell us approximately the size of the system that would generate about maybe 60 or 70% of what we want. So that's what Eric's talking about, is using this equation as a really quick way to figure out approximately what size do we need for that.
And John, before we move on, I don't want to slow us down too much here, but we got a quick question. If the system's rated at 25 degrees Celsius or 77 degrees Fahrenheit, what happens when the temperature is below 77 degrees Fahrenheit? For example, Wisconsin, it can get,
power goes up.
Yes.
They are more efficient in colder temperatures. And so as the temperature goes down, power goes up. And so one of the calculations that your installer is going to do is figure out what is the absolute maximum voltage when you have the minimum temperature. So they're going to look at that polar vortex and say, well, I can hit negative 30 C. If I can hit negative 30 C, what's my maximum voltage and power? And I got to match my inverter based on those numbers at lowest possible temperature. So they actually do better in cold temperatures. They do worse in warm temperatures. But the fact is, it kind of balances out because it's not a large difference. And a lot of times when it's warmer, we have more hours of sunlight. So our summers are still our best production time, even though we have higher efficiency when it's colder. So the best production is usually in the spring and the fall at any moment, any individual time period, because I've got cooler days and the sunlight is beginning to be more direct. Good question.
One more question based on this screen here. So based on the discussion we just had around estimating how many, what size system you would need for your home, how much area is required for a 300 kilowatt panel? So you could add another layer to your calculations there based on the square footage per panel.
Yeah, you could. We could go back and look at the exact numbers, but a solar panel is about 5.5 feet by about 3 feet. That's very rough, but you could get a more detailed version. So about 16 square feet approximately is what each solar panel is. And we could go back. And so in this case, there's 66 3/8 inch by 40 inches by 1 9/16 inches deep. The frame is that deep. So that was pretty rough. 3 foot is maybe a little rough because they're 40. This one's 40 inches, but you can get about 16 square feet is approximately what they are.
Yeah, and that number changes all the time in terms of the overall dimensions. But essentially, I think to get to David's question, you could take your specs for that 300 watt panel if it's 5 by 3, figure out how many square feet per panel, and then how many panels you would need. If you have a 10 kW system, and then you just divide it by that, and then that's how many modules it would take, and then you could, if you have, I don't know, 10 panels times whatever your square foot per panel is, that would give you the overall footprint, whether it's on the rooftop or the ground.
Yeah, and if it's there's only about a 1/4 inch in between solar panels. A lot of times when you have rows, you've got 1 inch between rows, and then you want, if it's a roof, you want at least a foot, probably 18 inches all the way around of roof space. So that gives you a little bit of sense that I have to have a little bit of space around the outside to meet the electric code. So some of those considerations. All right, we're going to get to the next slide. Another way to estimate production is to go through some of the online calculators. They also, they do probably a better job because they use more detailed weather data. This is one from NREL called the PV Watts calculator. This has some of the estimation calculations that we're going to, that exist in the SAM model, which we're going to use the detailed SAM model. So this is kind of the scaled down version, and it does a good job of estimating production. The economics in this particular calculator are not very good. So in this case, we're going to just simply select a location of where that is. Within a couple of miles is close enough. We're going to put in a system size, in this case 14.4, just like that previous system I had. We're going to tell it what the tilt is and which way it's facing. And so this case is facing south at an 35 degree tilt, and it's estimating 21,208. And so that's going to be, again, a pretty good accurate estimate, probably more accurate than that back the hand calculation. But again, I'm suggesting that this number is pretty accurate, that these numbers down here for production are not very accurate because they made a lot of assumptions. So use those with caution. You can feel pretty confident that this is going to be within about 5% of what's actually going to happen, as long as there's not any shade and things like that.
Just another note, John. That PV Watts calculator that you're sharing now, it does have a map overlay feature where you can put your address in. You kind of see it there in the bottom, yep, where your cursor is. You can put your address in and it'll pull up a satellite image of your property, and you can literally pin mark your rooftop and it'll estimate what the maximum size, what the maximum rated capacity would be of a system you could put on your rooftop. So
yeah,
just
so
kind of an FYI.
If you zoomed into your roof and you put 4 dots, and it would say that you could put this many kW in that space, and it would tell you approximately the largest system you could put in there. And again, largest system is not always the system size you want, but it's a limitation if you're trying to fit it on a roof. That's the biggest. So that feature is pretty neat. Okay, I just drew a couple of these. These are kind of simple line diagrams of what a system looks like, not within any of the wiring details. But this has 2 solar panels, but this could be 2 or 20 or 50. But essentially, you're going to need some type of inverter. This has got a string inverter on it because the solar panels generate direct current electricity, which is not compatible with your home or the grid. And so the inverter is going to turn that DC into AC. And it's going to turn it into AC that matches the grid, because alternating current has a sine curve, and it's going to match that sine curve perfectly. And then it's going to output AC this way. And then it's going to get used by your home first. And if there's excess, it's going to go out to the grid. And if you're not generating enough for your home, it'll use electricity from the grid. We're going to go over the details of that later, but that's generally the concept. Okay, let's look at a grid tied with a battery backup. It is important to note that in this system, if the grid goes out, the solar, this just shuts off, and it basically says, we're going to wait till we see the grid. So if you're expecting backup power from your solar array, you're not going to get it unless you put in the battery backup. I don't particularly like battery backups because they're expensive, and you really have to have a need for that backup to justify it. So that's one of your thoughts with respect to, do I really need the backup? What am I backing up? How much am I without power? Is that going to be a problem? And then maybe even price other backup options if you need the backup. In this case, to have that battery backup, I've added a couple of things. I added a charge controller, I added a battery, and I added a second disconnect. So if the grid is out, I can get completely disconnected from the grid, not having any risk of putting electricity on the grid, and I can run my load, home, farm, business, directly off of the battery or the solar as that happens. And so that's a system with a battery backup. we're going to touch on the three different types of inverters, and I'm going to start going a little quick because we got to get to the next step here. But there's three different types of inverters. There is where we put strings of solar panels on large inverters. It's called a string inverter. They have benefits in the fact that they're the lowest cost. They have disadvantages in the fact that if we were to shade one solar panel with a tree, we lost this entire row of solar panels because the way they're wired, they are not tolerant to partial shading of the solar array. So you can lose an entire row or maybe even the entire system if I shade only part of the system. I could lose the entire system for the period of time it's shaded. So they're not tolerant to partial shading. If they want to be roof mounted, it requires additional equipment. So typically on roof mounts, we do not see string inverters. But if you have a ground mount, string inverters are an excellent option because they are the lowest cost. And so that has that's a good thing. This is a set of microinverters. You can see that I don't have a large string inverter down at the bottom. Instead, I have individual microinverters under each solar panel. Those have benefits in the fact that if I do shade part of one solar panel, I only lose that one solar panel. I don't lose the entire system or half the system. So they are more tolerant to partial shading. They are the highest cost. And so you'd really, there's got to be a reason to put them in. They are excellent for roof mounted applications, partially because they meet the rapid shutdown requirement. Rapid shutdown means that if we lose the grid, they actually will shut the solar or any electricity from flowing all the way to that level. While if we go back to this one quick, if we lose the electric grid, this section of wire is still energized, and that could be a risk to firemen and other things that are messing around. So in the rapid shutdown, the new rules say we need to shut that down right at the solar panel level. The third type of system is a kind of a hybrid of the two. And what we have is optimizers up at the solar panels and a string inverter down at the bottom. These can also do partial shading, so we only lose the one if they're shading. They also can shut down at that level, so they meet rapid shutdown. They are intermediate in cost. They have fairly low equipment costs, but they are higher in installation costs because it's like I have to install both sets. I have to install the optimizer, which is like a microinverter, and a string inverter as well. But they can work out pretty well, and they are moderately common, but only one company sells them, but that company has had pretty good success selling those. So those are the three different types of inverter systems, and which one works for you really depends on what type of system you have. Is it roof mounted? Is it ground mounted? What kind of shading do you have? Things like that. Rapid shutdown is become an important consideration. Obviously, the electric code is always a consideration, but rapid shutdown has changed how systems look because we have to be able to shut down up at that solar panel level. And so really what it's led to is that most roof-mounted systems are microinverters or the optimizers, the hybrid systems, and only ground-mounted systems are string inverters. Though the string inverter companies are coming out with some electronics that can be mounted on the roof to make a string inverter work for a roof mount, but we are changing things over time with the electric code. And it's important for your installer to know the electric code. And so you want to be clear on that. All right, I'm going to turn it over to Eric, and Eric's going to introduce a system advisor model scenario, and I'll let him explain kind of his goals for that. I'm going to stop share. Go ahead, Eric.
Thanks, John. So as John outlined in the opening slide, our goal here today is to kind of give you an introduction to the system advisor model. This is a tool that we've really designed our bulletin series around. So the supporting resources that you have seen on the SARE website and that we'll be sharing with this workshop, those bulletins are really designed to position you to use this tool. This is a free modeling tool that's developed and maintained by the U.S. Department of Energy's National Renewable Energy Laboratories. And it is a very detailed model that, again, a free resource. It's just, there's a lot of power and information in this tool. With that said, it can be a bit overwhelming. And so our goal with this real quick tutorial on the first session is really for you to just sit back and enjoy the show. Don't try to understand, how to run the model necessarily this week, or I should say this afternoon. We just want to give you a sneak peek, and then we'll kind of work over the next couple sessions to learn more about some of the inputs. And then ultimately, when we get together during the fourth session, you should be a little bit better positioned to understand where some of this information fits into the model, and we'll revisit this and hopefully at that point do some more detailed analysis and some of the more advanced features within this tool. So when you open it, and you can see they do update it regularly. I actually need to run an update on my system here. You kind of go to this top corner and start a new project. They have a number of different types of projects that you can model with this tool. Now, John and I have used it pretty much exclusively for photovoltaic solar. So if you click the drop-down menu, you see there's a couple of different options. We would encourage you to explore the PV watts option as a starting point. The detailed PV model is very detailed, to the point where you essentially will be designing your own system in terms of speccing out specific modules, speccing out specific inverters, putting in your AC to DC load ratios, series and parallel strings. You'd be calculating all of that. And so it gets fairly complex pretty quick. But it's an outstanding tool obviously for developers to be using. For residential business, home farm, we kind of encourage you to start with this PV watts version. And again, as John mentioned, we tend to work with projects that fall under this distributed category. So projects that would be more behind the meter type development. You can see there's an option for residential owner or a commercial owner. The main difference there is going to be how some of the taxes and depreciation is handled. And so, obviously it's pretty self-explanatory. If it's for your farm or business, you would select a commercial option. If it's for a residential application, you would take that residential option. So we'll do a commercial project and come down here and click OK. And that takes us to the main page of the model. So again, it can be a bit overwhelming, but we're just going to kind of do a high-level overview of a sample here. It's fairly logical in terms of, or intuitive. You kind of start at the top left, and we just work our way down as we build this model through these different tabs. Some of these tabs have a little bit more information and a little bit more input that goes into them than others. But that's okay. It kind of walks us through the development process. So the first thing we need to identify is what's the location? And as John just illustrated, the importance of that is it really influences our solar resource, right? So I have a number of different projects that I've uploaded. If you're interested in putting in your own location, you can just type in your address or your longitude and latitude and download that into the library, and it'll default with a TMY. That's a typical meteorological year file. So it takes, I'm not sure how many years of data it compiles together, but 20, 30 years of data, and it kind of averages out the outliers where you have a year that may be unusually warm or cold. So one of the other things I wanted to just kind of point out, so you can see I've highlighted Dayton, Ohio, and it's looking at a 60-minute weather files in a 60-minute cycle, typical meteorological year. On the bottom down here, you can see it automatically fills in a lot of this data. John was talking earlier about the solar resource. You can see here, global horizontal irradiance for Dayton, Ohio is 4.15 kilowatt hours per square meter per day. And of course, you have your direct irradiance and diffused irradiance is broken down as well. You also see average cell temperature. So you get a lot of good information just from the weather file here. Just as comparison, if I would kind of go right above that, the Tallahassee, Florida, and click on that, you'll notice, okay, we've went from 4.15 to 4.91 global horizontal irradiance. So the solar resource is obviously going to be dependent on the location. And that's one of the things that we really like about this model is it takes into account all the minor details that are going to ultimately influence your production, and also those details that are going to influence the financials of this project as well. So we'll leave that at Dayton and kind of move forward here. System design. So the main thing that we see here right off the bat is the system size. So what is our nameplate capacity? How big of a project do we want to put in? You could use John's formula to estimate that or calculate that. I'm going to kind of use a project on a farm that we've recently worked with on a hog barn. It was a 25 kilowatt system, nameplate capacity, nameplate DC capacity. Now, you see there's a drop-down menu where you could put premium high efficiency modules or thin film or standard. Again, if you're really interested in the detailed version, you can actually select the brand and the model of module that you want to use. But for the purposes of this, we'll just leave it at a standard module 25 kW system. Now, the next area here, we can kind of select what type of a system is it. Is it a fixed open rack system? So that would be a ground mount system that doesn't move. Is it a fixed rooftop system? Single axis tracker, single axis backtracking, which is basically a single axis tracker that assumes no shading from panel to panel, or a dual axis tracker. So we'll go ahead and assume this is a fixed ground mount system. Actually, let's do a rooftop system. And so this barn was 412 pitch, so it had basically an 18-degree tilt. So again, if we're able to do a ground mount system, we can select the angle of the tilt, and oftentimes you'll use the latitude of the location to maximize that over the course of the year. That latitude you can get right off of your resources page that we were just on. But for a 412 pitch, it's going to follow the contour of the roof at 18 degrees. And then, the building orientations aren't always going to be perfect if you're doing a rooftop. So, this one was, let's say, is at 135 degrees. So we're not necessarily facing true south. And this is one of the things you can use the model to kind of compare. Is there a benefit from putting it on the ground versus on the roof if it's not ideal situations? System losses, we can use the defaults, typically get you pretty close. If you wanted to just kind of do a gross system loss estimate and put in a one overarching loss factor, you could do that. Or as you see here, NREL's itemized that based on the cause of that efficiency loss, and they've estimated it based on the data that they've used from demonstrated projects. So these numbers do change over time. If we have time on next Thursday, we might look at this 3D shade calculator, but essentially this is a tool that allows you to zoom in or overlay your site and estimate the impact of trees. So you can literally generate a tree on a site and estimate the size and how much shading impact that would have in absence of an actual shade loss calculation done by an installer. So we don't have time to look at that right now, but it is a pretty interesting feature. Grid limits, there's really nothing for us to look at here in terms of interconnection limits. We'll leave that disabled. Annual degradation. So as most materials exposed to sunlight, they're gonna, modules will degrade, so they'll have efficiency degrading over time. 0.5% annually is a pretty good estimation. And sometimes you can get that information off of the actual module itself. They have both product warranties that will warranty the modules against product kind of manufacturing defects, but then they also have performance warranties where they will estimate what the annual degradation will be and guarantee them to perform at a certain degradation rate. So if you know a specific module, you might want to zero in that number a little bit, but we'll leave that at 0.5% annually. Okay, the systems cost page. This one can be a little bit overwhelming because there's just so many different boxes. And if you step back and really think about what's happening here, this cost page is itemizing different components of the overall system cost. So how much of the cost is for the modules, how much is for the inverters, how much is for racking electrical components, installation labor, contingencies, permitting. So this information is rather helpful to developers. So if there's any installers or developers on the call that are interested in using this type of a modeling tool, this will certainly be helpful to you to kind of see where your cost allocations are going to rest. But if you're a homeowner or a business owner, you really don't need that information. And so I like to just go through, and sometimes this is just a helpful hint with this model in general. I like to zero stuff out and then start to repopulate it so I can see and understand what it's calculating. So I just real quickly go through and zero everything out until we get to the cost of zero, and then go back in and for this farm I was working with, they had a quote $2.10 per DC watt. So you can just simply put that in 2.10. Oops. 2.10, and while it's going to say all of that cost is allocated towards the module, it really doesn't matter for the purpose of the financial calculations for the cash flows table. They're just worried about what is the total installed cost, and then of course you can see it breaks it down on what is the cost per DC watt. And so that's kind of a nice trick or a way that you can kind of simplify this cost page if you're just looking at it for a home or business. Zero everything out, put in what you think the installation cost would be for the project, and that'll get you in the ballpark. Now you can't see
the reason those are different is he has the taxes 5% tax base. So if that's a with tax or without tax, you got to decide that.
So if you're in a state that is tax exempt, so in Ohio, there's no sales tax for solar projects in Ohio, I could go ahead and zero that out right here. It'll still show a tax rate at 5%, but it's assessing 0% of that. So that gets you back down to your $2.10 per DC watt, which is exactly what we put in up top. The other thing that we'll see on this page is your ongoing operations and maintenance. Now, we can do a lot of interesting things with this. For right now, we're going to kind of simplify it. You can see they've defaulted this at $16. And so this is a cost that's based it's a fixed cost based on capacity. So a fixed cost based on the system size. And basically what that's doing is saying for every kilowatt hour of nameplate capacity, we're gonna assume $16 per cost annually, for operations and maintenance cost annually. And then again, we'll look at some different ways that we can estimate this during the fourth session and get a little more detail, but we'll leave that there for now as a default. The financials page is a lot of the defaults are automatically populated for you, and then you can go through and edit them as necessary. So your debt percentage, 100%. Are we borrowing 100% of the money? If it's a cash purchase, you put that at 0%. If you're gonna say you borrow 60% and not 600. So you borrow 60% and put 40% cash into the project. It's just going to adjust your debt to equity ratio in the financials. You could have the loan term. So say it's a 10-year loan at say 3.85%. The analysis period is again something that you can adjust. Most of the time it's defaulted at 25 years, which tends to mirror kind of where the warranty periods follow with the modules themselves. We can adjust the inflation rate or the discount rate. We'll talk a little bit more about the impact of a discount rate and inflation as we think about the time value of money. It'll, again, default your federal and state income tax rates. You can adjust those as needed. Here you can see it said 5% system sales tax. We're actually 4.25 where I'm at. You can go back to that systems cost page. You'll see it's changed that from 5 to 4.2. But again, we're assessing 0% because it is exempt. So just kind of showing that if you paid sales tax in your state, that's where you would adjust that, and it would show up on that cost page. Insurance kind of assumes a 0.5% annually as a benchmark. Again, if you get a quote, you can adjust that up or down. I tend to look at the cash flow table and just kind of give it the eye test and see, is that reasonable? I've talked with a number of folks, actually one that's both in the ag sector, but sells insurance into the ag sector. And he kind of had a different way of getting to it. But at the end of the day, it was the same recommendation, which is about a 0.5% of the total installed cost. Sometimes I'll use a 0.25%, just depends. If you have property tax, and again, this will vary state by state. This is where you can input that information, and that's going to be one of those things that's going to be very different from location to location. And there's a couple different ways you could put this in. If you have the actual tax rate, you could put the tax rate and your assessment up here. Or if you've calculated your effective tax rate, then you could just leave it at 100% and put the effective rate here. But so where I'm at, we're at 4.02% and 35% assessment. I just wanted to put that in. Actually, where I'm at, we're exempt from property taxes, but I want to show where that comes up in the property or in the cash flow table. 5-year makers, we'll kind of leave that as the default here for depreciation. And again, we'll look at that closer on next Thursday. So that kind of completes our financial parameters. As we jump into incentives, kind of the cornerstone or the main incentive is the investment tax credit program. You can see labeled up top here. It automatically defaults at 26%. So that's automatically there. And then there's a whole bunch of other opportunities to put incentives in, and we can do them based on investment. So a specific amount. We could put in a percentage. So, a 25% grant. There's a couple of federal programs that we'll talk about. 25% of the total project cost. You could kind of plug that in. And this just helps you kind of itemize. Is it a federal program, state, utility, or other? You could put a capacity-based incentive in. So again, a dollar amount per size or per kilowatt, per watt, I guess in this instance. Or production-based incentives. An example there would be solar renewable energy credits. Some of you live in markets that do have SRECs available. Solar renewable energy credits are based off of production. So essentially 1 megawatt hour of production is equal to 1 renewable energy credit. In Ohio, I was kind of looking, the latest trading price for a SREC in Ohio was $13 per credit. So, and again, that's $13 per megawatt hour of production. So we would need to convert that to kilowatt hours to make this work within our incentives page. So take your 13 divided by 1,000. It's a state incentive program. We would put 0.013. And then you can put the terms. So is it a 10-year SREC? And you can sell SRECs in different ways. And so this will really be kind of a project by project basis. But say you locked it in at 10 years, $13, and you can just kind of leave that there, and it'll calculate that automatically based on the system size and estimated production. All right. Kind of moving through electric rates. This is a really useful tool, and they have a link to an external website here, or you can just kind of click this search for rates tab, and it is going to populate all of the different utilities that have rates. And then you could either filter by zip code. You can filter for a specific project. So if you had a utility that you were interested, just start to type it in, Wapakoneta, Ohio. You'll notice in the top right, this automatically defaulted as commercial only. And that's based on the fact that we started, if you remember when we started, we selected a distributed commercial system. So if you selected a residential system, it would default as residential. You can click that to select all schedules, but essentially it's just filtering down to a rate schedule that would most likely apply to your project. So we'll leave that at commercial. The other thing you can do is click this box to only show the active rates, and it'll filter out some of the old ones. And then you'll just have to kind of look at your bill and match that with the rate that's there. But we'll say it's single phase general service. You can see there is a demand charge here that they've got described. But if you click the bottom here, download and apply, it'll automatically apply that to this model. You can see it gives you the note that it's been successful. So that kind of gives you a good starting point. What I've found, and I think John would echo this, is this is a good starting point, but a lot of times you'll need to go through with your electric bill and actually fine tune this or maybe refine it a little bit. And it allows you to do that. It just kind of inputs this, and if you wanted to change, your cost per kilowatt hour, say that looks high, you take it right off your bill and you can adjust that as you need to. When we talk about net metering, there's a couple of different ways that net metering is applied and or calculated. We'll look at this a little bit closer again next Thursday. I will say that the help menu, this is a good opportunity to kind of demonstrate that. The help menu does a really good job of pulling up this menu right based on where you're at within the model. And so you can see right here, net metering and billing. This will give you a definition of each of those different options. And so if you weren't sure which one to select, if you read through these bullet points, it'll pretty quickly clarify, okay, based on the net metering rules of your utility, which one of these you would need to select. So for my project, it's going to be net energy metering with dollar credits. And if you were to read that help menu, it would tell you that it's going to do month-to-month net metering. So it'll net meter over the course of the month. Any excess generation at the end of the month will be compensated based on the sell rate. And so this is where you would put that in. In Ohio, where I guess in this specific case, they would be compensated for net excess generation at avoided cost, which was, we'll say 4.5 cents a kilowatt hour. So we just kind of plug in 4.5 cents a kilowatt hour. You can see they have a different tier here. So this would be a tier 1, tier 2 is based on the actual usage. So there's a different cost for the first 1,000 kilowatt hours versus every kilowatt hour after that. You could also add different periods based on time of use. And so you can get pretty detailed with this. As an example, if I had, say I had a different rate for mid-afternoon in the summer, I could select 3 entries and put period 2 and put a higher rate. Say we're really high, we're 26 cents a kilowatt hour during weekdays. June, say 1 through 6 o'clock, June through August. You could just select that, type the number 2, and that's going to give you a different rate based on that period. So you can get very detailed with your time of use rates, whether that's seasonal or hourly during the day, and construct some pretty unique rate structures within this, which really gets more accurate as we estimate the value of a unit of energy. So I'm going to kind of put that back to 2. Energy escalation up here, it allows you to account for if you believe energy prices will increase over the 25-year period, you can estimate what that value will be. Keep in mind, we've already included 2.5% inflation on our financials page. So this would be energy escalation that would be above and beyond normal inflation. I typically do 0.5% to 1.5%. Normally I'm closer to 0.5 to 1%, I guess. But so we'll plug that in there. And then I just wanted to show real quick, I'm not going to do anything with it, but you can see that they've enabled demand charges here. So they do have demand rates in addition to energy. And that's just going to be based on when the farm sets its peak demand. And you can, if you don't have demand rates, you can just kind of click that box and it would disable that. Demand rates are really important to understand, especially when you're working with farms or businesses, as it relates to the overall financial impact of the project. And it's really important when you think about demand rates to understand your load profile, not just from a monthly perspective, but from an hourly perspective, because installing solar will not automatically decrease your demand. If you're on a demand schedule that's estimating your monthly demand, in Ohio, most of our farms are on a 15-minute rolling window. Some of them are on a 30-minute rolling window, but it's looking at what is your largest demand spike over a 15-minute window in that billing period. So you may have great solar production during the day, but if ventilation fans and feed auger motors and well pumps kick on after the sun goes down, you're just going to move that demand occurrence to later in the day. And so it's important to understand your load profile if you have a demand rate. So finally, I guess the last thing I'll show here is we can get really detailed with our load profile. So this is looking at, how does our home, farm, or business use energy? You can select this sub-hourly option where you can actually change the time setup. This is entered automatically at 60 minutes. So 1 hour intervals. You could get down to 15-minute intervals if you'd like. One quick note though is the time intervals for your load profile need to match the time intervals for your weather data. And so the weather data files that we uploaded were automatically on 60-minute intervals. So I would recommend trying to match a load profile at 60-minute intervals if you're trying to use that detailed data. And again, this is most important if you have a demand rate. If you just have a monthly, energy bill and demands aren't a big part of your cost structure, that's not as important. You can click this button over here to the right that says, let's just normalize our supply profile to our monthly electric bills. And then it's got some defaults there that obviously are not going to be accurate. So you click the edit value, and this is where you could take your 12 months electric bills and just plug them right in here, kind of January through December. And I'm going to do this longhand. This is, I guess, an opportunity to mention that the System Advisor Model works very differently between Macs and PCs. So if John were doing this demonstration, he would just cut and paste these in. It doesn't work as well with a Mac. So I'm going to real quickly just kind of estimate the monthly usage off of this farm.
I always forget that you can't cut and paste with that.
Yeah, I do too.
Yeah, let's, Eric, I think when you get done with that, I think we're ready to at least look at the output and just kind of briefly look at it and look at the, we won't necessarily discuss the output a lot in great detail. We'll just look at it and look at least what they provide in the output. And then we'll go to questions.
All right, we got everything in there. Hit OK. You can see it's put in our kilowatt hours, and then it's estimating our peak kW demand. And so at that point, we're all the way through the model on that top left side. So we come down to the bottom here and just hit simulate. It's going to run some calculations, and it gives you this nice summary table right off the bat to kind of look at some high level data. So, what is our annual energy output over the course of the year? Capacity factor, which that's rather low, so we need to go back and kind of look at that. Part of that could be based on the fact that it was 18-degree tilt, not necessarily true south. a couple of different financial metrics. They use levelized cost of energy. They look at net present value. We see simple payback and discounted payback. And so what we're seeing there is the impact of the time value of money. So as you change the discount rate, it's going to change, the net present value. It's also going to change your discounted payback period. But you can see right off the bat, this looks like a pretty good project on the surface, right? So we see a positive net present value of 13,900, a simple payback of 8.2 years, or if we account for the time value of money, that would be a 13.8 year payback. And then you can see down here our debt to equity ratio, where we said, well, we're going to borrow 60% and put 40% cash equity into the project. So the last thing I'll show, and because we are short on time here, I really like with this is it provides you a nice cash flow table that allows you to just go in and kind of spot check stuff, right? So we talked earlier about operations and maintenance costs. You can see O&M expense right here. You can kind of go through and just kind of spot check. What did we account for? How much were we assuming insurance? And then that helps you kind of understand, okay, are we overestimating? Are we in the ballpark? And then this is something, again, that if you have a PC, you can export this directly to Excel with your formulas. So you can follow the formulas in terms of how it's doing the calculations. If you have a Mac, you can export it to Excel, but it doesn't, at least unless they've changed it in the update, it doesn't take the formulas with that. So, but it is kind of helpful to have the ability to put that into an Excel sheet and really understand those numbers. And so with that, I'm going to stop here. I'll just say that that's the tip of the iceberg. There's a lot of powerful simulations that we can do once we get this base constructed. But that's what Sessions 4 is about. We're really thinking that it might be helpful to at least get a sneak peek of what the model looks like. That way, as we look at Thursday's materials and next Tuesday's materials, you can start to think about, okay, I know where that might impact the model. Yeah, I see why that information is important because it could fit in or influence this model under that section. And then we'll tie it all together on the fourth session. So with that, John, I will stop share and turn that over to you.
Thanks, Eric, and appreciate going through that. I think it's important to recognize that might have been a little overwhelming to go through it at this time, but we're seeing all these different inputs and how they impact. What we're going to do now is we're going to go to questions, but what I would like you individually to do is click on the link in the chat that I just put in, and that's going to take you to this site. It's a Google form site, and on this Google site, it's called a Google Jamboard. I want you to answer these questions, and this way we don't have to necessarily do that in the chat. We can actually see it. So to do that, you might go and click on a sticky note and say whatever you want to say, and then it will add that sticky note up. And so then you can add those up and start to see what other people say. So what are some reasons for installing solar on your farm and business? And what I want to know is, what are your motivations? Why are you interested? Why might other people be interested? And so start adding some of those to that. You can also do some handwriting stuff in, but the sticky notes I think work pretty well. There's also a second question and up at the top, there's two, and you just switch over to the second question. And so you could answer some of those as well if you want. I'm just going to kind of watch these and make some comments as I see them. But what I will also do is say, if you have questions, this is a good time as people are putting these up to type questions in the chat, or even unmute yourself and ask questions. So go ahead and let's do that for a few minutes. And I'm going to watch the Jamboard, make some comments, and then Eric and I can kind of watch the chat and answer questions. I'm really liking what I'm seeing as far as reasons, because I like that there's a diversity. What I dislike is when the utility says, well, these aren't a good deal because they don't pay back soon enough. Well, that's an oversimplification, because what if a person has a goal of having green energy? The payback is not their primary priority. it's a secondary priority. And so I really like that we're seeing a mix of those things. All right, the question from Steve is, without a backup battery, as the sun goes down, the generation slows and then stops, correct? If we're looking at monthly use of electricity in the calculations, we are not accounting for use during nighttime hours for fans, feed augers, and so on.
I can take that, John.
Yeah, go ahead, Eric.
Yeah, you're correct, Steve. And we actually have a hog barn here in Ohio that we have some advanced energy meters installed on, and they have a 12 kW PV solar system installed on the rooftop. And yeah, so we're collecting data points every 5 minutes, and they're on a demand rate. And so one of the things that we've noticed as we look at the load profile is, the hogs are active for, typically a couple hours after their solar kicks off for the day, where you still see feed auger motors cycling on and off, well pump motors kicking on and off. This is a naturally ventilated barn, but obviously if it were a tunnel barn, you're going to have your tunnel fans, especially during the summertime, running as well. So you're correct. That type of activity, you're not necessarily going to reduce your demand. Now, that's in terms of accounting for that. That's where it goes back to when I was mentioning within the model. If you're simply plugging in monthly kilowatt hour usage into that model, you're not accounting for the demand impact. The model can't accurately determine, is your demand at the same time as when your generation is. So with that said, if you have hourly usage data and you can plug in, or I guess in a sense you wouldn't have to do it manually, but you could import that hourly 60-minute energy usage data, then the model would actually be able to look at it and see, based on when they're using energy and based on the weather data that shows when we're going to be generating, are we offsetting demand? So the model can do that, but the way that I just estimated it, it won't with that example, because you need that additional information. So that's a good question for a developer or for an installer. If you have demand rates on your farm, is, has your modeling accurately compared your hourly weather data so that we see hourly production to the hourly load profile on our farm, so that we know what are the impacts of demand rates on this? Because I can say in most instances with confined animal housing, demand charges really make a tough economic case for installing solar.
All right, we're seeing some really good comments here, and what again, really liking the diversity. We've got a couple of comments about kind of remote areas where I don't have electricity, and using solar as that option to provide some energy at that site. And that could be a small amount for like an electric fence, or it could be a larger amount for maybe an off-grid cabin or an off-grid barn or something like that. We're not going to talk in great detail about those off-grid systems, but a lot of the ideas apply, and we would just simply apply the cost of the system and what we would maybe value for that electricity, and we might be able to compare that to other generators. We're not going to cover that in detail in this webinar, but I think you'll learn a lot that'll help you be able to do that. I also like the independence and security. And I like that because, again, just looking at economics doesn't give us all of the reasons why we might want to do this. And being more independent and feeling more independent are real things. And it is important to some people to have that. And there is increasingly at least some option for some different levels of backup power, even without batteries. I have a very limited version of that at my home system, where I have one outlet that I can run up to whatever my solar is generating during the day on that one outlet if the power was out. So I can switch it over to kind of an off-grid mode and run that one outlet. It's not real attractive, but if I had a 5-day outage, I could keep my refrigerators cold, and I probably could keep my freezers cold because I could run them 4 to 6 hours during the day, and would work out okay. It would work out okay. So it's not a great situation, but it does exist. So those are excellent. I'm going to switch over to the second page. This is kind of people responding to the model in and of itself. Which aspects of the modeling do you think have the greatest influence on the results? The results being the economic output results, but the ground versus roof is going to impact the production. It's going to impact the orientation. The orientation of itself, which direction does it face, it does make a difference. The discount rate and the rate structure, that one I think is extra important, and we're going to see that as we learn about how to use those, and then we'll actually be able to model and look at the influence of those as we model that on Thursday. So we can alter the discount rate and look at how that impacts the output.
And one of the things that I think is important to remember is sometimes when you really dive into the weeds of that model, sometimes you can get overwhelmed and you start thinking to yourself, wow, are we really splitting hairs here with 0.25%, allocation for annual insurance and O&M and energy escalation rates, and individually, yeah, a lot of those things probably don't make a huge difference in the overall performance of the project. But what happens is, if you start to overlook those details in aggregate, they make a big difference. And so it is important to look at a lot of those things that, well, it might only be a couple $100 here or there annually, but at the end of the day, when you add all of those up, it does make a big difference in terms of how the financial performance anyhow of a project might look.
Yeah, I'm going to add to that. We had a person just bring up upkeep and cost to maintain, so the operation and maintenance cost. What I sometimes like to do with this model is create kind of a best case scenario and worst case scenario, and say, what if my operation and maintenance was very low, and what if it was about as bad as it could get? Maybe I had to replace the inverter at year 12. Or all the inverters at somewhere along the line, something like that. And then I could run both scenarios and feel much more confident in the fact that my economics is going to fall somewhere in that range. It's not likely going to be the best case scenario, and it's not likely going to be the worst case scenario. It'll be somewhere in between. But by running some different scenarios like that, I can feel more confident that this is going to perform like I expect it will, somewhere in this range. And so we don't necessarily always have to be exactly right, but also we want to be reasonably conservative with our numbers so we're not making it look good. And I can tell you that I have seen some quotes that are very, very rosy, and they will say, well, you're never going to, operation and maintenance is zero, insurance is zero, the electricity is going to inflate in price by 6 or 7% a year, to even 10% a year. Well, all of a sudden my economics look awesome. It'll never happen, but it looks awesome. And that's what we're trying to avoid, is be more conservative and say, we feel like it'll be at least this good. And if it's better, great. If price of electricity goes up at a faster rate than we estimate, you're in good shape to do better on it. But we don't want to make this look overly rosy for reasons that we can't justify. And so that's really what we're getting at.
One of the things I really like about a couple of the notes here, John, as I look at them and try to kind of compartmentalize them in my mind, is it really highlights what's the beautiful part of that model. Is on the top side here, you see a couple of examples, ground versus roof and orientation. So these are design characteristics that are going to impact how many kilowatt hours are we producing, right? What's our yield, as your earlier slide was looking at. So, and then on the bottom side, we see discount rates, operations and maintenance, system updates and upkeep. those are more on the financial side. And that's the nice part about this model is when we look at the bottom line and how long it takes to pay itself back, this model takes into account both sides of that equation, the production variables and the financial variables, and brings them all together in that cash flow table, which is, you know, one of the important components or the valuable components of that model.
We're going to wrap it up here. We look forward to your questions in the future, and we will see you on Thursday for the next web seminar. Thank you for joining us. Thank you to North Central Region SARE for sponsoring this, and have a wonderful Tuesday, and we'll talk to you later.
Thanks, everyone.